Hi everyone, in this video we're going to talk about related rates, which will finally put our knowledge of derivatives to good practical use. So before we jump into some really fun problems, let's see how the setup's going to go for us today. So suppose x and y are changing. And this isn't so unexpected right now, but here comes the kicker. They're both changing with time. They're both changing with time. So what does this mean? This means that x and y are functions of time. Yeah? X and y are both going to be functions of time in this problem. Suppose we have that 3x squared plus 2y squared is equal to 5. Yeah? How can we find dx dt? Well, first, before we jump into just the mechanical part of this problem of finding it, let's talk about what does dx dt really represent. Remember, dx dt is a derivative. It tells us the slopes of tangent lines, but in the context of related rates questions, dx dt will tell us the instantaneous rates of change. So in words, this tells us the rate at which x is changing with respect to time, whatever x is. Okay? So how can we go about finding dx dt? Well, we need to differentiate with respect to t, both sides of your equation with respect to time. And before we do this in this setup, if we put t's in the problem, it will make more sense. You'll see it better. If we write this instead as 3 times x of t squared, right, because x is really a function of time, plus 2 times y of t squared equals 5. Really what it's asking for you to find is x prime, right? So let's differentiate both sides of this green equation with respect to time. Well, what's the derivative of 3 stuff squared? It's 6 stuff times the derivative of what's inside, which is x prime of t. Yeah? Plus, what's the derivative of 2 stuff squared? It's 4 stuff times the derivative of what's inside, which is y prime of t. And the derivative of the right-hand side is just the derivative of a constant, which is 0. And so now, we can easily see that we can solve for x prime of t, right? Just with some algebra. What would this look like if we didn't introduce the t's? You know, rewriting the equation with t's, maybe it might just add more variables that we don't want to look at. Most people would just differentiate with respect to t in this equation. So let's see how that would go if we try to do it up here instead. What's the derivative of 3 stuff squared? It's once again 6 stuff, right? Nothing's changed. And now we multiply by the derivative of what's inside with respect to time. And what's the derivative of x with respect to time? That's dx dt, right? So they're exactly the same, they just look a little different. Plus, what's the derivative of 2 stuff squared? It's 4 stuff times the derivative of what's inside. What's the derivative of y with respect to time? That's dy dt. And once again, the derivative of the right-hand side is 0. Often we will keep it in this form. We won't introduce we won't rewrite x and y as function of times. But this is really what's happening in the background here. So don't let this sort of notation confuse you. Once we get to this step, you say, boy, gee, howdy, here's dx dt, right? That's what I want to solve. And then your algebra spidey senses kick in. And let's solve it. Yeah? We subtract 4y dy dt. And then we'll divide by 6x. So we get dx dt is negative 4y times dy dt, whatever that is, divided by 6x. And so if we knew values of dy dt and y and x, we could find the value of dx dt. Let's see who cares. Let's put this in a real problem. I've already written the problem out. Hopefully it's legible, but let's read it together. Suppose oil is leaking into the ocean. This is a sad problem. At a rate of 100 centimeters cubed per hour, cubic centimeters per hour. So pretty slow. Forming an oil slick in the shape of a 1 centimeter deep circular cylinder. Find the rate at which the radius of the oil slick is changing 9 hours after the leak began. So what's really, really, really important in all of these problems is draw a picture. Right after we read the problem and we're sure that we kind of understand what the question's asking, we need to draw a picture. If you don't draw a picture, I really have no idea how to work the problem. So if you were to ask me to solve these questions without giving me a pencil and some paper, I'd be lost. So let's begin by drawing a picture. This is our step 0, really. Yeah? Here's our little, pretend that's a circular, slick, and it has some thickness to it. Yeah. Here's our little disc of oil. And what's coming into our disc of oil? We have some flow of oil, right? We have some incoming volume. Let's call our incoming volume V. But I don't tell you how much volume I've put in, I tell you the rate at which it's coming in. So what information have I given you? I've given you the rate at which the volume of the oil slick is changing, haven't I? The oil slick is adding volume at a rate of 100 cubic centimeters per hour. So really, what's the information that I've given you? I've given you dV dt, the instantaneous rate at which the volume of the oil slick is changing. Yeah? And that's variable. What else is changing in my oil slick? It's asking something about the radius, right? So let's be sure to draw the radius of our oil slick. There's our R. What's the height of our oil slick? It tells you in the problem that it's a constant, and it's always going to be fixed at 1 centimeter. Yeah? What's really important here, whenever you draw your pictures, only label constants things that will never, ever, ever change in the entire problem. If things are changing, do not put it as a constant. Yeah? Make sure that things that are changing get variable names. Yeah? So, what do we know? We know that there's some incoming volume, right? And it's coming in, the rate at which the volume's changing with respect to time is 100 cubic centimeters per hour. Okay? What else do we know? It also tells us that we're looking for the radius of the oil slick 9 hours after the leak began. But we don't know the rate at which it's changing, right? That's what we're looking for. We're looking for the rate at which it's changing. So it's not clear how to go find the rate. So what do we do at this point? Let's relate. So we need to probably find out what R is. Yeah. And we really, really, really want to know what is dr dt. What is the rate at which the radius is changing? Oops, dr dt. Sorry about that. So we need to go probably find the radius, and we definitely need to find dr dt, the rate at which the radius of the oil slick is changing. So what we need to do now is relate what we have to what we want. So what relates the volume of a cylinder to its radius? Well, there's only one equation that I know of. I know that the volume of a circular cylinder is pi r squared h, right? And here, because the height of the cylinder is fixed in the entire problem, h is 1. So I really know that the volume is equal to pi r squared. Yeah? Well, how do we find dr dt at this point? We can go ahead and find dr dt. I need to differentiate both sides of this equation with respect to time. Remember, v is changing with respect to time, pi is a constant, r is changing with respect to time. So let's differentiate both sides with respect to time. Pause the video, make sure you know how to do that yourself. So, differentiating the left-hand side, I see dv dt. What's the derivative of pi stuff squared? It's 2 pi stuff, right? Times the derivative of what's inside. which is dr dt. I know what dv dt is, I don't know r, and I don't know dr dt. But if I know r, then I can go ahead and find my dr dt, right? So how can we find r? Well, here we are. Let's use this equation here. How much volume has, what's the volume of the oil slick after 9 hours? That I know, right? If 100 cubic centimeters are being added every hour, what's the volume after 9 hours? It has to be 900, right? So I really know that 900 is equal to pi r squared. So let's solve for r. What does r have to be now? R has to be 30 divided by pi. And what are my units? Units are going to be centimeters. Yeah? Oh, sorry, square root of pi. 30 divided by the square root of pi. Everybody's favorite number. And now that we have r, we can plug that in and solve for dr dt. So let's do that. I know that dv dt is 100 equals 2 pi times 30 divided by the square root of pi times dr dt. Yeah? So what do we get here? Whenever we solve for dr dt, we get that dr dt is equal to 100 divided by 60 times the square root of pi. And my units here, well, what are my units? It's the rate at which centimeters are changing with respect to time. My time is in hours. So my units are centimeters per hour. Yeah? Good. Let's do another example together. Suppose a martini glass has the shape of a right circular cone that is 4 inches deep and has a diameter of 6 inches. If the glass is being filled with water, of course, at a rate of 10 cubic inches per second, find the rate at which the water level is rising whenever the water level is 2 inches deep. So before we jump in, let's remember the steps that we want to use to solve this problem. Yeah? What are our steps? Step 1, or step 0 really, right? The most important step is read the problem and draw the picture. Let's draw and label the picture together, yeah? We want to draw and label a picture. And remember, whenever we label things that are constant throughout the entire problem, you can go ahead and label as constant, but things that are changing must have variable names, okay? So draw and label a picture. Step 2 is find a formula, or an equation that relates what you have to what you want. Now find a formula that relates what you have to what you want. And this relation that you find is why it's called related rates. Yeah, because two things are changing and they're related by this equation that you'll find. What's step 3? Differentiate and solve for what you want. Yeah? So first we need to draw and label a picture, find a formula that relates what you have to what you want, differentiate, and solve the problem. And remember, solving the problem, you might have to go back to your original formula to find values that you don't quite know. So let's put this into practice, yeah? All right, so let's go back to our martini glass. What's step 1? Let's draw a picture, right? So here is my super cool martini glass. Yeah. There it is. Beautiful. But I don't really care. I mean, the stem, it's wonderful, and I know that my art is lovely, but we really don't care, right? What we're really looking at is the portion that's being filled with water. So let's kind of zoom in on the part that we care about, which is this inverted right circular cone. Yeah, here's my inverted right circular cone. That's being filled with water. And I know that I have some water coming in, right? It's being filled at a rate of 10 cubic inches per second. So what's coming in? I have some volume that's coming in at a rate of, 10 cubic inches per second. Yeah. What do I know about the glass? I've told you the dimensions of the glass. It says that it is 4 inches deep. And it tells you that the diameter at the top is 6 inches. And I really want to know the rate at which the water level is rising when it's 2 inches deep. So the trick here in our picture is to draw some water. Yeah? Suppose we have a little layer of water down here. This is some red water that we've poured into our martini glass. What do I know about the height? And really remember here, am I going to label my height as 2? No, because the water level is changing as the water goes up, right? If the water level is changing, I have to label it with a variable, okay? If you went ahead and labeled it with 2, you would not get the correct answer. You have to call it a variable name, and we'll plug in constants at the very end. And what's going to be the height across here? Or sorry, the distance across here. That's twice the radius, right? That's our diameter. And the trick here is going to be similar triangles, okay? The trick here is going to be similar triangles. I see my big cone has an angle here, yeah? And my little cone shares the same angle. These two triangles formed by the cross sections have to be similar. So what does that mean? The ratio of the sides is the same. I know that big diameter divided by small diameter has to be the same as my big height divided by my small height. Yeah? And let's put that aside and see how we can use that. This is one equation that kind of relates what we have, but it doesn't, I haven't factored in the volume that's coming in, right? So what equation relates volume to radiuses and heightses? Yeah? I know that the volume of a cone is 1/3 pi r squared h. Okay? And I know that in this particular cone, this ratio is true. And what information is this 10 cubic inches per second coming in? That's a dV/dt, right? I've also told you, let me scroll up a little bit. I've told you that dV/dt is 10, yeah? Volume's increasing at a rate of 10. And what am I looking for? I'm looking for dH/dt, yeah? Whenever h is equal to 2. That's all that I've told you now. So what relates, this equation relates what we have, something about volume, to what we want, which is something about the height. But you notice that we have two varying quantities here. This is single variable calculus. We need something to reduce this to one variable. And this is what's going to do it for us. This similarity relationship here is going to allow us to get rid of the radius, because I only want it to be about the water level, which is the height. So in this equation, let's solve for the radius. What does r have to be? Well, r has to be 6h divided by 8, which is 3h divided by 4, right? And with this, we can plug it into my volume equation and get a single variable function, yeah? Or a function with only one changing thing on the right-hand side. So what does that give us? That means that volume will be equal to 1/3 times pi r is 3h over 4 squared times h. And let's simplify this. We get that the volume is equal to 3 times 3 is 9, divided by 3 is 3, over 4 times 4 is 16, pi h cubed, because h squared times h is an h cubed. Now what can we do? If I differentiate both sides, I'll get a dv dt, I'll get a dh dt, and then we can solve the problem. So go ahead and pause the video, see if you can figure this out yourself. Alright, so in what little room I have left here, maybe here, let's differentiate this equation. We see that dv dt has to be, what's the derivative of 3/16 pi stuff cubed? It's going to be 9/16 pi stuff squared times the derivative of what's inside, which is dh dt. I know dv dt, I know h is 2, right? And now I can solve for dh dt. I think whenever we plug everything in, well, let me just do it here. I see that I'll get dv dt is 10, should equal to, h is 2 now, right? Now that I've differentiated, I can go ahead and plug in for h. So h is now 2, that's the point that I care about. 2 squared is 4. 4 divided by 16 is division by 4. So we get 9/4 pi times dh dt, right? So what's dh dt? Finally, dh dt is equal to 40 divided by 9 pi. And what are our units? It's a rate at which a distance, or length, right, h, which is in inches, is changing with respect to time. Time in this problem was measured in seconds, right? So our unit is going to be an inch per second. Okay. Cool. Let's do another problem. Oops, car B. All right, so let's read this problem together. Car A is traveling west at 50 miles per hour, and car B is traveling north at 60 miles per hour. Both cars are headed toward the intersection of the two roads. At what rate is the distance between the cars changing when car A is 0.3 miles and car B is 0.4 miles from the intersection? So pause the video, try to draw the picture yourself, try to relate and label, right? Label everything. Relate what you have to what you want, and then try to solve the problem. Yeah, give it a shot yourself. All right, so let's draw the picture. Here's car B, and car B is traveling north. Yeah. Car A is somewhere here, and car A is traveling west. And I know that they're headed for their intersection. Car B is traveling in this direction, car A is traveling in this direction. And it's asking something about the distance between the cars, right? So let's draw a line between the cars to represent our distance. And I know what you're thinking, boy gee howdy, this is north, right? This is west. What's the angle here? It's a right angle. Yeah. So we have a right triangle. And let's label our directions now. What do we want to call the length between A and the intersection? Let's call that distance x. What do we want to call the distance between car B and the intersection? Let's call that y, both of which are changing. And let's say that the distance is capital D. And now what relates x, y, and d, given that we're in a right triangle? Pythagorean theorem, right? We know that x squared plus y squared is equal to capital D squared. And what information has it given you in the problem? It's told you that dx dt, that's the rate at which this distance is changing. What's the rate at which distance x is changing? It's 50, right? But it's not 50 because x is getting smaller. So what's the rate? It's really negative 50. It's really negative 50. And what's dy dt? We know that car B is traveling at 60 miles per hour, but what's the rate at which y is changing? It's getting smaller, isn't it? So it's really a minus 60. And both of these are in miles per hour. Yeah. And what are we looking for? We really want to go fetch dd dt. That's why I call it a, if I did lowercase d, it'd be kind of confusing there. Yeah. So how do we find dd dt? We differentiate this equation with respect to time on both sides. Differentiating on the left, what's the derivative of stuff squared? It's 2 stuff times the derivative of what's inside with respect to time, which is dx dt, plus 2y dy dt equals, and remember d in this problem is changing, yeah, so we can't fix it right now. So it's going to be 2d times dd dt. Yeah, sorry that got a little crammed over there. That says dd dt. Okay. Do I know what x is? Now at this point I can start plugging values in. At the point that I care about now, I know that the length of x is 0.3. I know the length of y is 0.4. I know dx dt, I know dy dt. The only thing that I need to find now is capital D, and I can find dd dt now. How do we find capital D? How do we find capital D? Let's scroll up. Well, we need to go back and use our original equation. Yeah. I know that 0.3 squared plus 0.4 squared is equal to capital D squared. What does that mean about capital D? It's 0.5, right? And with this we can now solve for dd dt. Let's go ahead and plug in. I know that x is going to be 0.3, dx dt is negative 50, plus, oops, times 2. 2 times, what's y? Y is 0.4, times dy dt, which is negative 60. Yeah. And I know that this quantity has to be twice d times dd dt. So this has to be equal to 2d times dd dt. But we know what capital D is now, don't we? What's capital D? It's 0.5. So whenever you plug in 0.5 and you solve for dd dt, I think you should get that dd dt is equal to negative 78. Yeah, and what are our units here? D is measured in miles. Time is measured in hours. So we get miles per hour. Cool. All right, guys, so I hope that this helps. This should give you enough of an idea to start the homework. This takes a lot of practice. This is certainly not an easy concept right now. So be sure, try to draw the pictures yourself, write down equations that relate what you have to what you want, differentiate, and try to fill in the gaps and solve the problems. Yeah, I'm happy to help in any way that I can. Please never hesitate to send me an email. We can set up a time to Zoom, and don't forget to come to the live office hours during your class time. Yeah, this takes a lot of practice, and I'm happy to help in any way that I can. So I look forward to seeing you in class time, and I look forward to all of your questions, and I'll see you in the next video. Thanks so much.